So thank you for listening to this talk. I am going to talk about an approach to obtain tight lower bounds for contraction problems, and in particular for the Hadwiger number problem. So we will start with a short introduction with some background for this study. So first of all, to define the Hadwiger number problem, we need to define the notion of a minor. So we say that a graph H is a minor of a graph G if there is a series of operations that we can perform in G in order to obtain the H. These operations include edge deletions, edge contractions, and vertex deletions. So let's see this in this example. So first we are going to delete some vertices and edges in G. So we obtain the following graph. Now look at these sets, the colorful sets. So each one of them is connected. So we can take a spanning tree in each one of them and contract the edges of the spanning tree. Then after doing so, we obtain the following graph, which is exactly H. So here we get that indeed H is a minor of G. You can also think about the notion of a minor as follows. So we say that H is a minor of G if we can find pairwise disjoint connected subset of G. These are these colorful subsets in these examples, that we can map them to the vertices in H. Each colorful subset gets mapped to a different vertex in H, such that we connect them by edges as dictated by H. So for example, if we map the blue subset, it is mapped to the topmost vertex in H, and the red subset is mapped to the rightmost. They notice that in H there is an edge between them, so there must be an edge between this connected subset in G. If in H there wasn't an edge between them, then in G there might be an edge between them, but we don't have to have this edge between them. So now the definition of the Hadwiger number of a graph G is as follows. So this is the largest integer G, H, such that the click on H vertices, denoted by KH here, is a minor of G. So in this example, you can see that we have here a click on 5 vertices, which is a minor of G. But the click on 6 vertices is not a minor of G, so the Hadwiger number of G in this example is 5. This problem can be trivially solved in time n to the order n, because in such running time, you can actually guess these colorful, disconnected subsets and how they should be mapped to the vertices of H, and also check whether you have the appropriate edges. And then there was an open problem whether this is optimal, and in particular, whether we can solve the problem in time 2 to the order n, so in single exponential time. This was asked in several venues. So before we go on to discuss this particular open question, let's look at a more general problem, which is called the graph minor problem. So here we have two graphs, G and H, and we ask whether H is a minor of G. So the graph minor project is actually the inspiration behind the field of parameterized complexity, and the graph minor problem is central in this project, and also it is central to other research areas as well. If you want to read more about this problem and in general about the graph minor project, you can look at the recent survey that we have. It is cited here. So what is known for this problem on general graphs is the following. So it is fixed parameter tractable, FPT, parameterized by the number of vertices in H, we denote it by little h. What it means is that this problem is solvable in time, f of h times some polynomial in the input size, where f is some computable function of h. Also, what is known that unless the ETH fails, this problem is not solvable in time n to the little o of n, even when n is equal to h. So this means that under the ETH, the trivial algorithm that we saw before is actually tight. So notice that we are in particular interested in the case where age is the clique. This is essentially the Hadwiger number problem. So now, to understand the context of this study, let's talk about three related problems and see what is their status. So the first one is the subgraph isomorphism problem. Here we are given two graphs, G and H, and we ask whether G contains a subgraph that is isomorphic to H. So whether G has a copy of H. So for this problem in general graphs, the following is known. So it is W1 hard on the general graph, unlike the previous problem, the graph minor problem. So this means that it is unlikely to be FPT, that is unlikely to be solved in time f of h times some polynomial in the input size. This problem can be solved in time n to the order h. I remind you that n is the number of vertices in G and h is the number of vertices in the graph H. And actually this is tight. In the following sense, under the E3.A, it cannot be solved in time n to the little o of n, even when n is equal to h. So G and h have the same number of vertices. On clique, the problem stays W1 hard. In fact, the clique problem is a very famous W1 hard problem in the parameterized analysis. But it can be solved in a single exponential time, in 2 to the order n. Now let's look at another problem, the graph homomorphism problem. So here we are also given two graphs G and H, and then we ask whether there is a homomorphism from G to H. This means that we should map the vertices of G to vertices of H. And we can map some vertices of G to the same vertex in H. But if two vertices in G are adjacent, then the vertices that we map them to should also be adjacent in H. So for this problem on general graphs, it is para-NP hard. This means that it is NP hard even when H is equal to 3. So in particular, we don't expect it to be FPT parameterized by H. However, it can be solved in time H to the order n, and this is also tight under the ETH. We cannot get H to the little o of n. When the situation is that H is a clique, then this problem is equivalent to H coloring, where we seek a proper coloring of the graph in H colors. So it is para-NP hard still, even when H is equal to 3, because then we have the 3 coloring problem, which is NP hard, but it can be solved in time 2 to the order n. Then we might also be interested in the case where G is a clique. Then this problem becomes equivalent to subgraph isomorphism when we swap the roles of G and H, and it can be solved in time 2 to the order H. Now the third problem is the topological graph minors problem. Here we are given two graphs G and H, and we ask whether H is a topological minor of G. So here by topological minor, we mean that among the operations that we can perform in G, we can only contract edges incident to at least one vertex of degree 2. And as before, we can delete edges and delete vertices. Alternatively, you can think about it as if the connected sets are singletons, so we just map vertices to the vertices to vertices, and when we map edges, the edges in H, then they can be mapped to paths in G, and the paths should be vertex disjoint. So maybe this problem can be thought of as the closest relative to the graph minor problem. So for this problem, what we know on general graphs that it is FPT, and it can be solved in time n to the order n, and this is also tight. So unless the ETH fails, we don't have n to the little o of n, even when n is equal to h. But when the graph h is a clique, it can be solved in time 2 to the order n. So this should be a big O. And it is also FPT because it was even FPT in the general case. Okay, so let's summarize what we saw so far for these related problems. So we saw that subgraph isomorphism, graph homomorphism are not FPT, topological graph minor is, and Hadwiger number is. Here we're only talking about this problem in the case that age is a clique. And we have single exponential time algorithms for subgraph isomorphism, graph homomorphism, as well as topological graph minor. But what was open is whether we have such an algorithm also for graph minor, for the Hadwiger number problem. So now let's go to discuss our contribution. So what we saw is that the answer here is no. So unless the ETH fails, the Hadwiger number problem cannot be solved in time n to the little o of n. So in particular, we don't have 2 to the order n time algorithm. Moreover, one consequence of this is that unless the ETH fails, the clique contraction problem, where we want to contract at most k edges in a given graph to get a clique, this also cannot be solved in time n to the little o of n, and this is another open problem posed in the literature. So more generally, we saw that our approach works for the following, for some problems of the following form. So we define the F contraction problem as follows, this with respect to some graph family F. So given a graph G and a non-negative integer t, we ask whether we can contract at most t edges in G in order to obtain some graph in the family H. So what we saw is that all of the following problems, all of the following F contraction problems for different families F cannot be solved in time n to the little o of n in under the ETH. So this includes clique contraction, which we discussed earlier, chordal graph contraction, where we want to contract at most t edges in order to get a chordal graph, and similarly, interval graphs, proper interval graphs, threshold graphs, perfect graphs, trivially perfect graphs, split graphs, and perfect split graphs. So our approach consists of a sequence of reductions. Now, in the last part of this talk, I will discuss some technical details about this sequence of reductions. So you can see that here we have the clique contraction problem, and here we have all of the problems that we mentioned earlier. In particular, Hadwiger number is here. So each one of these arrows describes a different reduction. So now let's move to talk about some technical details. So let's start with the first reduction, where we saw hardness that we cannot solve in n to the little o of n, a problem called properly colored least subgraph isomorphism. So the least subgraph isomorphism problem is defined as follows. We are given two graphs G and H that have the same number of vertices, as well as the list of vertices in H for each graph, for each vertex in G. So each vertex in G has a list. And then we ask whether G contains a subgraph isomorphic to H, where each vertex in G must be mapped to a vertex in its list. So it's like subgraph isomorphism, but we have the constraint that the vertex in G can only be mapped to a vertex in H that belongs to its list. So it was known that unless the ETH exponential time hypothesis fails, this problem cannot be solved in time n to the little o of n. Now we defined a special case of this problem that we called the properly colored least subgraph isomorphism problem. So here the difference is that G and H are properly colored. This is how the input looks like. So in the input, we also have these proper colorings of G and H. And moreover, for every vertex V in G, all the vertices which belong to H and are in the list of V have the same color as V. So we have this additional restriction on the lists. Then we showed that unless the ETH fails, even this special case cannot be solved in time n to the little o of n, and this new property will be useful. I will try to give some intuition about the place where we use it soon. Okay, so this was the first reduction. So here first you can see a problem called properly colored list subgraph homomorphism. So along the way, to get through the properly colored list subgraph isomorphism problem, we go through this first problem. This is also the case in the reduction that we base our reduction on. So now let's go to another problem that we called cross-matching. So in the cross-matching problem, we are given a graph L with a partition of its vertex set. So it's not a bipartite graph necessarily, it's just that we have some partition of its vertex set into two sets A and B. And we ask whether there is a perfect matching between A and B, whose contraction in G is a clique. So we want to contract edges that go across A and B. So let's see what is the relation between this problem and the list subgraph isomorphism problem that we have just discussed. So to see this relation, think about the following construction of L. So suppose we were given an instance of list subgraph isomorphism, and now we will construct the graph L as follows. So on one side, this side A, the subgraph induced by A will be just the complement of G. So if there is an edge between two vertices in G, so here we don't have this edge, and if there wasn't, then here we have an edge. And the other side will be just edge. Now, the crossing edges are defined as follows. So we have an edge between U in the complement of G to V in edge, if V belongs to the list of U. Now, how is this related to list subgraph isomorphism? So first of all, notice that when we are talking about a perfect matching between A and B, this is what we seek here in the cross-matching problem, then this can be thought of as a mapping of G to H. So the crossing edges define the mapping, how we map G to H. Now the second thing, notice that in the cross-matching problem, we want to obtain a clique. So here it means that in order to get a clique, that we need to map the non-edges in the complement of G into edges in H, so that eventually we get a clique. So this means that the edges of G should be mapped to edges of H. So this sounds like isomorphism. But there is a certain difficulty here, which is the non-edges in the complement of G, we might fill them in another way, not by edges in H. We can fill them by crossing edges. But to argue that this cannot happen, this is the point where we critically use the proper colorings of G and H. So if you want to look to read more about this, you can look at the paper. This is the point where it is used. So now we saw the relation between cross-matching and list subgraph isomorphism. Now let's see what is the relation between cross-matching and clique contraction. And also a certain a variant of it, which we call the noisy structured clique contraction. So what is the relation to clique contraction? So in one direction, it is easy to see it. Notice that a solution to cross-matching is clearly a solution to clique contraction. So if we have an instance of cross-matching and we have a solution there, it will also be a solution for this instance when it is thought of as an instance of clique contraction, because in cross-matching, we also want to contract edges in order to obtain the clique. The other direction is not clear, because in cross-matching, we must contract edges that go across the parts A and B, not any edge that we want. So a solution to clique contraction might not be a solution to cross-matching. So what we do in the reduction is that we add some vertices and edges to the graph in an instance of cross-matching, such that we enforce our solution to be perfect matching between A and B. When we want to get a clique, then we must contract edges between A and B and not any edges that we want. Moreover, we also saw that if we add some noise to the very highly structured graphs that we construct, they don't cause any damage in a sense. So noise means that we add some more vertices and edges between these vertices, and also edges between these vertices and the vertices that already exist in the graph. what already existed, this is referred here as the core. So it has limited effect in the sense that it is not helpful to try to contract these new edges in order to eventually fill the edges, the non-edges in the core to obtain a click. So now let's talk about the last part, where we have reductions to several contraction problems. So for example, here we have a single reduction to something that we call non-trivial chordal contraction, which already captured many graph classes. And here we have also 3 other reductions for this problem: Hadwiger number, split contraction, and complete split contraction, and perfect contractions. But all of these reductions follow similar lines. In particular, depending on the contraction problem at hand, the noise might be slightly different, how we define the noise here, but the proof technique is essentially the same. So we first show that the core must yield the click. For example, if we are talking about chordal graph contraction, so we want to get a chordal graph after contraction, we show that it is necessary to contract edges so that the core graph will become a click. And then, in a sense, the noise becomes irrelevant. Okay, so we saw the background for this study, what are the results that we obtained, and at the end we saw an overview of the main idea that we used in order to obtain this result. So thank you again for listening.